Good afternoon. I'd like to welcome everyone today to yet another talk in our Curious Minds series. And today we're very excited to have on hand Michael Strevens from New York University. And Michael is here to talk about his book, The Knowledge Machine, How Irrationality Created Modern Science. And I found this a fascinating work, and I think you will too. And I hope you rush out to your local bookstore and get it. So to introduce the topic today, I want to share my screen for just a bit. This is, as I said a second ago, a part of our Curious Minds series. And now normally these events have been held on our campus, although now they are held virtually, more or less, although next semester I think we will be going back to in-person events. And there you see our beautiful campus and some previous events at which speakers have talked with our students about their works. The whole series here is premised on the ideas that writer Gerald Graff once said, that talking about books or ideas is as important educationally as are the books and the subjects themselves. And I think you'll find this to be very true with regards to Michael's book, The Knowledge Machine. Some upcoming events we have next week on Friday, the 25th of February. Now notice the time is 12:30 rather than 12 noon. We have Susan Wolf Murphy from Texas A&M Corpus Christi to give a talk on her book, Bordered Writers. And the talk is on Latinx students and their literary practices. In 2 weeks, on Friday, March the 4th, also at 12:30, Steve Davis and myself will be hosting a book study discussion group on Dorian Linsky's book, The Ministry of Truth, the biography of George Orwell's 1984. So that should be a lot of fun. But for today, we have Michael Strevens on hand, and Michael will talk for, approximately 40 minutes or so, and then he will take questions and answers afterwards. As he talks today, as he's talking with you about his book, maybe consider some of these questions. Why is modern science so successful? Why is it so much more powerful than, say, ancient Greek science, which was equally systematic and concerned to explain the things we see around us? Does a scientist have to have a special kind of personality in order to do their job well? Another question, how does it matter that science is a social institution, not just a bunch of people trying to figure stuff out? And how does today's talk perhaps cause you to rethink your views on science and or the scientific revolution? So again, during the talk, feel free to type questions about Michael's ideas in the chat box at the lower right-hand corner of your screen, and then I'll cut and paste those into the chat for everyone to see. And then when Michael is done, we will have students, faculty, staff, and community members ask questions through the chat box. And I think it should be a fascinating talk today. So Michael Strevens, our guest today, was born and raised in New Zealand. He moved to the United States in 1991 to undertake a PhD at Rutgers University. Currently, he teaches philosophy of science at New York University. His academic work is principally concerned with the nature of science, covering topics such as scientific explanation, understanding, complex systems, probability of various sorts, causation, and the social structure of science. He also applies contemporary research in cognitive psychology to explain aspects of both philosophical and scientific thinking. In The Knowledge Machine, a trade book, he explains why science is so successful at creating knowledge and why it took so long for humans to figure out how to do it right. So without any further ado, welcome, Michael, and we look forward to your talk today.
So what then is modern science doing differently? That's the kind of question that I, as a philosopher of science, am always asking myself, and the question that I set out in this book, my book, The Knowledge Machine, to answer. And here's a two-part answer to that question. First of all, modern science, by contrast with not just the Greek science of Aristotle, but with Chinese science, with the science of the Islamic Golden Age, with the science going on around the same time in Europe, what we call in Europe the Middle Ages. What modern science does differently is it looks for a special kind of observable fact. So not just concerned with the observable facts in general, but a special kind of observable fact. And second, and I hope to explain to you how this is related, it excludes from scientific argument everything that is not an observable fact. Okay, so there's a kind of a narrowness to science, to the rules of doing science, if you like. A narrowness that in fact is so extreme that I think of it as being in principle irrational. Now, it's a good thing. This narrowness is a good thing. It's what gives science its power. And yet at the same time, technically speaking, it's irrational. I say that not to disparage science, as you now know, but to, grab your attention and then to focus it on this exclusionary methodology that we find in modern science. Okay, so this is pretty much the plan for the rest of my talk today. First of all, to talk about that special kind of observable fact, and then to talk about the role of narrowness in finding these facts and bringing them to bear on theories. So beginning with number one, the special kind of fact. Let me put all this in terms of a story, an example that I use quite a bit in my book. It's the story of the fruitful scientific interaction between these two figures. You may very well recognize the one on the left there, Albert Einstein, the formulator of the general theory of relativity, a whole new theory of the way that gravity works that supplanted Newton's theory. In fact, that according to which there really is no such thing as a literal force of gravity, but rather the things that Newton attributed to the force of gravity has to do with the curvature of space and time. Now, I'm not going to don't worry, I'm not going to give a talk about special relativity, but this was an exciting new idea Einstein put in its final formulation about 1915, 1916, living at that time in Switzerland, right in the middle of Europe, as when you think about those dates, 1915, 1916, a ferocious war was going on around him. A war in which Einstein, who was himself German, was culturally identified with one side, ultimately the losing side. There sitting right next to Einstein, you have the English physicist Arthur Eddington, who, of course, would at that time have been on the other side of the front lines from Einstein, neither of them fighting, thank goodness. In any case, this new theory of gravity that Einstein formulated in the middle of the war immediately grabbed Eddington's attention. Eddington was a very sophisticated mathematical physicist. He saw right away how interesting Einstein's theory was, and he wanted to test it. As it happened, right after the war ended in 1919, there was going to be an opportunity to perform this test to see if Einstein's new theory of gravity was correct. And what's being done in this test is to detect the amount by which gravity, or rather Einstein's substitute for gravity, gravitation, you can call it to be kind of neutral, is able to bend light rays. So the thought is this, that when, say, the light from a star passes by the sun, and we really need, this effect is very small, so we need a really big object if we're going to perform this experiment properly, something with a lot of mass. And the biggest object we have around here is the sun. So the idea is to see what effect the mass of the sun has on the light from distant stars passing right by the sun. So what you want to do is look at the light traveling from a star that's almost directly behind the sun and see the degree to which that light is bent. The effect of the bending is going to be to make it look like the stars around the sun are pushed out a little bit. So they'll be a little further apart from one another than they would be if you just looked up in the night sky when the sun was nowhere near around. The thing is, though, that the sun is, as well as being very massive, is also very bright. So the only way to really get a bead on these stars, to measure their positions accurately enough to test Einstein's theory, is to look at them when something is blotting out the sun, Luckily, the Earth has a moon that from time to time does exactly that in a total solar eclipse. So Eddington's proposal was to take advantage of the fact that in the middle of May 1919, there was going to be a total solar eclipse that was going to travel across this part of the world. What you see here is a broad band showing the places where the sun would be partly eclipsed, and then a very narrow dark band, and that's where there's going to be a total eclipse. Eddington suggested an expedition that would travel to several places along the narrow band and take these photographs of the stars around the sun at the moment of the eclipse, which was the moment of totality, which is going to last about 5 minutes, and then compare those photographs with photographs of the very same stars when the sun was nowhere around, and by comparing the photographs to measure the degree of bending, and therefore test Einstein's theory, which predicted a very particular value for the bending, which is different from the value you might have expected from Newton's theory. Okay, so this is what happened. The Eddington team selected a couple of places to travel to. One is a location in the north of Brazil, Sobral, there in the South American continent, and then also an island off the coast of Africa, Principe. And they sailed off in 2 teams to make their measurements. Here's a picture of the setup they had in Sobral in Brazil. They couldn't take complete telescopes with them, so they just took the lenses, stuck them in some tubes, and then laid the tubes out flat, as you can see, and used the mirrors which are in the foreground. So those are, you're looking at the backside of a couple of mirrors, like shaving mirrors. The mirrors point at the sun and they reflect the sun's light, or of course in this case more exactly the light from the stars around the sun, down the barrels of the telescopes, and at the other end there are cameras that capture the exact position of the stars. So here is the kind of photographic plate that you would get from this. In fact, this is one of the photographs from this eclipse experiment. And maybe if you look, this is a negative, so the dark and bright are switched around. The big white disk in the center is the eclipsed sun, which of course to our eyes would look black. Around it, the black fringe is the corona of the sun, which would look very bright. And then maybe you can see just a little bit up and right of the sun's disk, you can see a couple of lines. Those are lines that Eddington or another one of the experimenters has drawn in, so you can find the position of the stars, which would show up as tiny black dots in between those lines. Not so easy. Anyway, here's a remarkable fact. The kind of difference the experimenters were looking at for, the kind of difference that would reveal whether Einstein's theory was correct or not, or whether rather Newton's theory was correct, which predicted a slightly different position of the stars. That difference is just a fraction of a millimeter, so a tiny fraction of an inch. It is, in fact, something like a 60th of a millimeter, if you know what that means, or about would that be a 300th of an inch? So a microscopic distance, but this tiny, tiny difference, which would just barely be perceptible when the Eddington team superposed these photographs and used all their fancy techniques for detecting something so small. That would be what would tell the difference between these 2 theories that had completely different stories to tell about gravity. Or take a different experiment. This is another experiment which also tests Einstein's theory, but one that actually only returned a positive result in 2015. This is the LIGO experiment, or rather it's one part of the LIGO experiment, which is supposed to detect gravitational waves. It took a long time and a lot of money to build this experiment. The development, the idea was first pitched in the 1960s and 70s. The development of the experiment, which involved building 2 of these facilities that you see here, got underway in the 1980s. The funding was almost cut off for this experiment in the early 1990s. Then finally it got back on track. They built these things, and this, when I say funding, we're talking hundreds of millions of dollars, because these gravitational waves, like that tiny difference in the positions of the stars, are, to detect them, we require an apparatus that's incredibly sensitive. To build something that sensitive that excludes many of the normal kinds of vibrations that would set off the equipment really just takes a lot of time and costs a lot of money. Once the LIGO experiment got going in 2002, it still detected nothing at all. In fact, it detected nothing for 8 long years until it closed down for an upgrade. Then finally, when it reopened in 2015, it saw, as it were, 2 black holes colliding. And that was the evidence that scientists were looking for gravitational waves as predicted by Einstein's theory. So these 2 experiments, the eclipse experiment and the LIGO experiment, different in certain ways. The LIGO experiment is on a much grander scale and is far more expensive. Still, we're in both cases looking for tiny little differences, tiny little changes, a little movement of the stars in one case, a slight, very, very slight vibration in the other case. That would be the kinds of changes that would actually tell you whether Einstein's theory was right or not, whether gravity really worked the way that Einstein said it did. And this is the kind of special observable fact I have in mind when I say modern science looks at a different kind of fact than the sort of thing that Aristotle looked at. I'll give you one more example of this, and just to get away from physics a little bit. Okay, this is an island in the Galapagos Islands off the coast of Ecuador. The famous Galapagos Islands that were very inspiring to Darwin when he was formulating his theory of evolution. As it happens, a couple of evolutionary biologists, Rosemary and Peter Grant, decided to use this island to observe the populations of the finches on the island, again, which had originally been very inspiring to Darwin, to keep track of the populations over many years. And in fact, the Grants have been going back there since 1973 every summer to camp on the island. It's about half a mile across and about as inviting as it looks in this photo, just to observe those populations. And they observe them so closely, they know the identity of every single finch on the island, which is a rather remarkable thing. Here they are, a fairly recent photo, looking not too bad. Obviously, those summer visits were refreshing, even if not a whole lot was going on the island of Daphne Major. In any case, in the course of making these observations, they began to suspect that they had actually observed the evolution of a new species by hybridization, if you happen to know what that is. I won't go into the details. It took a long time, but finally, in around something that they'd begun to notice in 1981, so when they'd been going to the islands for a mere 8 years, finally, after tracking this bird for a number of generations and doing appropriate analyses and so on, in 2018, so this is now 40 years later, they were able to conclude that they had in fact observed the species, which is a remarkable thing to actually see, not just evolution in action, not just see natural selection in action, but to see a new species appear, but obtained by dint of rather remarkable effort on the part of the Grants. Okay, so that, of course, is a very brief sampling of some of the sorts of things that count as evidence in modern science. And you'll see that in these examples, and also this is so much the case elsewhere, the kind of evidence that scientists find to be incredibly fruitful for thinking about, for deciding between theories, is often science that looks not at the broad configuration of things, not at qualitative phenomena like rainbows or meteors, the kinds of things that Aristotle was concerned about, but at very small details, facts that require extremely close observation or prolonged observation, as in the case of the finches, and often of quite complicated structures, the details of quite complicated structures. Because of this character to the evidence, it is often very time-consuming to obtain, very expensive to obtain. Furthermore, very risky to obtain. Things can easily go wrong. So you might, and in fact this did happen in one of the 2 locations where Eddington was photographing the stars at the time of his eclipse. It simply might be cloudy. What you require is clear skies for 5 minutes, and if you don't get them, then this whole mission has been in vain. Or you might run out of funding before your whole apparatus starts working. That's what almost happened with the LIGO experiment to detect gravitational waves. Or the Grants could have visited those islands for decades and seen not a lot that was particularly interesting going on. Okay, so on the one hand, this is the special kind of fact, but it's a special kind of fact that raises a certain question about how scientists get motivated. I think on the one hand, science is so successful because it's able to uncover these facts, because scientists themselves are able to devote the kind of time and attention and money to digging up the facts, as I put it here. But on the other hand, you might wonder where science manages to get the kinds of people who would be willing to actually carry out these operations from. Where do you find people who are willing to go and visit the same arid little island in the middle of nowhere for 40 years running, or to sail off to the tropics in the hope that for a crucial 5 minutes, the skies are not going to cloud over? Where are these people coming from? Are these a very special kind of obsessive person? No, I mean, there are hundreds of thousands of scientists. Most of them are completely ordinary people. Something has made them has given them a kind of a motivation, an ability to focus, a desire to focus on these little facts, no matter what, or almost no matter what the risk, no matter how much effort is required, and therefore turn them into the kinds of people who will dig up the things that science needs to progress. Now, I'm coming to the end of the first part of the talk, and I'm going to turn to this question of the fact that scientific argument excludes everything that's not observed fact from its arguments. And that, I think, in that exclusion, in that narrowness, lies the answer to the question about how scientists get motivated to devote the kind of effort they do to finding the critical but hard to get facts. So I'm going to talk about this narrowness of science as a motivator. And in writing about this, I've been very much inspired by the ideas of the famous philosopher of science, philosopher and historian of science, Thomas Kuhn, who you see here. I can't tell you about Kuhn today in the short time I have, but I can at least quote him saying, and this I think is a very insightful observation, there's something about the rules of science that force scientists, and I'll just read the quote, to investigate some part of nature in a detail and depth that would otherwise be unimaginable. So this is what I've been telling you about. This detail and depth to the investigations of the Grants, or to Eddington and his team sailing off to photograph the eclipse, that strikes us as something that we may be glad somebody is doing, but something we would, almost none of us would ever bring ourselves to do, or so we imagine. Kuhn is saying the reason that scientists do this, what pushes science forward, is a kind of a rule or set of rules that really gives scientists no choice. This is what force means here, I think. Scientists have no choice if they want to be scientists than to follow the rules, and the rules give them no choice but to embark on these rather extraordinary evidence-finding missions. Now, the rule that lies really at the heart of science is what I call in my book Science's Iron Rule, to give it a sense of, I guess, strictness and even a slightly punitive aspect, which is perhaps appropriate. And this is a rule that, if you're going to sum it up in 4 words, these I think would be the words: only empirical evidence counts. To say just a little bit more about what's in the rule, what you find is, on the one hand, first of all, the rule lays out what counts as an empirical test for a hypothesis, what counts as a relevant observation or experiment. And I'm not going to say any more about that side of it, because I really want to focus on the narrowness. But then, and here comes the narrowness, it says nothing but these kinds of empirical tests. So just the kind of things you imagine when you think of scientists empirically testing things, like observing the lives of the finches, following the lives of the finches, trying to see how the apparent positions of the stars change, that kind of thing. Nothing but that counts as a good scientific argument. And in the rest of the talk, I'll explain why. I do want to remark that this prohibition is, in fact, one way to put it would be a kind of a speech code rather than a prohibition on what scientists are able to think. In fact, scientists can think whatever they like. There's no restraint that the rules of science put on what is going on in scientists' own heads, and it's kind of hard to see how any such rule could be effective anyway. What can be restricted, though, is what goes into the scientific journals, which is where scientists publish all of their results. And it's only by publishing their results they get credit for their results. So by imposing certain rules on what can appear in the journals, you impose certain rules on the way scientists communicate with one another. And that's why I call this prohibition a kind of a speech code. Okay, let me explain how it works. Let's go back to the case of Eddington testing Einstein's theory. Now, Eddington, as I say, was a great mathematical physicist, and really mathematics was his métier. He was a prize-winning mathematician at Cambridge University. Not such a great experimentalist. He was virtually fired from the Cavendish lab when he was doing experiments there. But his mathematical abilities gave him the insight he needed to see that Einstein's theory had a kind of a beauty and elegance in its explanation of physical phenomenon that was really quite unparalleled. And I think we can say without too much exaggeration that Eddington kind of fell in love with Einstein's theory because it was so beautiful. And I'm not going to show you the equations that he actually fell in love with, but here, if you like, is a graphical representation of a little piece of relativity looking rather lovely. Okay. Now, Eddington could, given both his talents, his dispositions, the reasons for his own commitment to Einstein's theory, he could have devoted himself to arguing in its favor, to trying to convince other scientists that they should go along with Einstein and accept his theory. He could have done that by sharing his perception of its beauty, by showing them how it solved certain explanatory problems that were left unresolved, or rather arbitrarily resolved in Newton's theory, and pointing to the elegant way in which it solves these problems. As you can see, I'm kind of shuffling around, actually explaining what the problems are, just to so as not to start giving another talk entirely. But if you'll just give me the benefit of the doubt, here is Eddington. Also, by the way, Eddington was a very talented writer and turned a great popularizer of science in the end. So he was perfectly set up to be the kind of person who would be able to persuade scientists to accept Einstein's radical new theory on the grounds of its mathematical beauty. But this, here's my punchline, this is exactly the sort of argument that is banned, prohibited in the scientific journals. Eddington, of course, can say what he likes to scientists privately, but it's simply not possible to publish a paper in a scientific journal saying you should believe this theory because it's so beautiful, because it's so elegant. And therefore, Eddington had no choice if he wanted to convince scientists to accept the theory, and he very much did. Incidentally, another one of his motivations was to create a kind of rapprochement between English and German science right after World War I, when there are a lot of rancor still existed. But in any case, if he was going to convince scientists to believe it, he had to argue using an empirical test. He had to actually get on the boat, and it was this precise boat, as it happens, the steamer Anselm, to get on the boat and sail off to the tropics on a journey that took to get to the Brazilian location about 2 months, spend another month setting up the apparatus, all in the hope that during the 5 minutes of totality, the sky would be clear, which in the end for Eddington, it wasn't on Principe. This I see as the narrowness of the iron rule, saying, forget that beauty stuff, give me empirical evidence, forcing a scientist to do not what comes naturally, but something that actually comes rather unnaturally, which is what in the end turns up those little numbers that ultimately push science on, in this case, by beginning to assemble the empirical evidence for Einstein's theory. Well, here's another example of the same thing. Now, more looking at the big science side of this. Here's Murray Gell-Mann, one of the originators of the quark theory of matter, saying in a public lecture, not publishing in a journal, beauty, simplicity, and elegance are, his words, a chief criterion for the selection of the correct hypothesis. So Gell-Mann believes that beauty is a sign of truth, as I think Eddington did. At the same time, and this is just a kind of statement of the iron rule, we find a physicist like Brian Greene writing in his book, The Elegant Universe, aesthetic judgments do not arbitrate scientific discourse. Ultimately, theories are judged only empirically. Now, Greene and Gell-Mann are not disagreeing with one another. Just take a moment for that to sink in. Gell-Mann is saying beauty is a sign of truth. Greene is not disagreeing with that. All he's saying is that whether it's a sign of truth or not, in our science journals, we don't appeal to it. We appeal only to empirical evidence. And I think they're both right. Gell-Mann about beauty as a sign of truth, and Greene about how the science journals work. Well, of course, being a professional scientist, he knows very well how they work. So here's one of the great discoveries that Gell-Mann made, just to develop this using a particular example. When Gell-Mann was thinking about this huge profusion of fundamental particles that were being discovered in the 1940s and 1950s, especially once physicists started to build powerful particle accelerators that could crash particles into one another, which created showers of new particles of all different types. Gell-Mann was trying to tidy up this profusion of particles by creating classification schemes. And one of his classification schemes looks something like this. Actually, it's a it's a classification scheme which looks much better in many dimensions, but I have to flatten it out here to fit it on the screen, and I've compressed its beauty down to a rather unexciting triangular form. I just have to again ask you for the benefit of the doubt here that there's a kind of a symmetry to this arrangement that immediately jumped out and really appealed to Gell-Mann. As he arranged 9 different particles, the named particles here corresponding to these nodes in this grid, into his beautiful mathematical structure, and then noticed there was one space in that structure that was unoccupied. No particle had been discovered that would take the place yet in this structure. So Gell-Mann, thinking that beauty was a guide to truth, predicted that such a particle would exist. Not just to show how smart he was, but because if this theory of his was ever going to get any currency in the scientific literature, he would have to provide an empirical test for it. That's what the iron rule demands. Now, Gell-Mann on his own, unlike Eddington, could not test the theory. Instead, what he in effect did was unleashed hundreds of people spending hundreds of millions of dollars at particle accelerator facilities like the one at Brookhaven in Long Island, not too far from where I am sitting giving you this talk, that ultimately discovered this particle, the omega minus particle. Okay, so this again is a case where the discovery of a theory is made by following clues laid out in terms of mathematical beauty. But the argument that's made for the theory in the official scientific journals can't be based on beauty because of the iron rule. And therefore, this forces scientists to do something that is far more arduous and far more expensive, building a particle accelerator, building the detectors and so on, but exactly the kind of thing that ultimately pushes science onward. So here we have the demand for empirical evidence, focusing all of scientists' energy into a particular kind of pursuit. You can, if you like, think about science on the view I'm suggesting here as a kind of a game, a serious game. The point is not just to amuse yourself, but to figure out how the universe works. But still a game in the sense that it has certain rules. You can only if you play the game, you have to follow the rules. You can only make legitimate moves, and every legitimate move, the iron rule says, is an argument using observed facts. So Maybe I should say, of course, a part of the game is coming up with the theories in the first place. But in terms of arguing for the theories, it's all got to be a matter of giving empirical arguments based on experimental tests, observations, or what have you. So scientists want to play the game for all sorts of reasons, including, finding out what the universe is really like. If they're going to play the game, though, they have to follow the rules, and this means they've got to throw everything they've got, as I put it here, into digging up the evidence. And that's where the motivational structure, that's how the iron rule works, as a motivational structure that pours all of a scientist's effort and energy when they're arguing for their theory into this empirical game, either like Gell-Mann finding predictions that will test the theory, or like the many experimental physicists who actually delivered the data that tested the theory, building experimental apparatus, running it, debugging it, and so on and so forth. Okay, that's my story about how narrowness operates as a motivator. I'll just take a couple of minutes to suggest, to make good on my promise at the very beginning, in my title, that this narrowness is in a certain sense irrational. Okay, here we're going to be looking back over a number of things I've said already. So first of all, many physicists do believe that beauty is a guide to truth. We have Eddington, we have Gell-Mann, who I quoted earlier, and here are a couple more quotes from physicists saying, testifying to their belief in the importance of beauty, not just as something that's nice to have, but as something that actually gives you a clue about what's right. Now, the iron rule, as it were, in spite of this commitment to the guiding power of beauty, says we may not have it. There's just the very same words of Brian Greene saying aesthetic criteria are simply not used in scientific argument. That's public scientific argument in the journals. Only empirical evidence counts. Okay. So we have a situation where, on the one hand, scientists themselves believe, or many scientists, that paying attention to beauty is really helpful in deciding what to believe. And at the same time, they're involved in this institution, science, whose official form of communication, where they publish their arguments, imposes a rule that we must pay no attention to beauty, which means, in other words, that the iron rule is saying we must ignore what physicists themselves believe is a powerful and readily available source of information. And that is what I take to be, on the face of it, irrational. To ignore, you want to solve a problem, you have some great information that will help you solve the problem, and then you just pay no attention to it whatsoever. Technically, it violates what we philosophers call the principle of total evidence. Okay, now I'm just about done. So, although this is a kind of irrationality, it's still, and this is the other half of my title, of course, a highly effective kind of irrationality. It's a narrowness that in a philosopher's sense goes too far, but has this incredible motivational power, which is exactly what allows modern science to harness these kinds of evidence that Aristotle, for example, simply could not get his hands on. So science works so well, I'm saying, because, or in part because, it operates according to a rule of communication, for communicating argument that's irrationally narrow. This goes some way, I think, towards explaining why modern science is so recent, why someone like Aristotle didn't conceive of doing science this way. To create modern science, somebody had to have the thought, wait, these irrationally narrow rules actually work really well. And that's something that, as you might imagine, did not come easily to the human race's preeminent thinkers. Okay, well, I'm just going to leave you with that thought, leave you with the thought that's behind my title. Here's the book if you want to know more. Thanks very much for listening.
All right, thank you, Michael. And I'd like for everybody to type any questions that you've got into the chat box, and I'll share those. And while you're doing that, I'll start with the first question. You can go ahead and quit sharing your screen if you want. Yep, that's great. All right. So my question is, Michael, the talk kind of provoked this. Does only scientific knowledge count as knowledge? You're muted. You're muted.
Gotcha. Okay, now I should be audible.
Yeah,
Uh,
you're good.
uh, I don't think so. I think scientific knowledge is some of the best knowledge we have, but we can gain knowledge about things without being part of the scientific infrastructure. And in fact, we can gain knowledge from some of these arguments that wouldn't be allowed in the scientific infrastructure. So I myself, I mean, I'm a philosopher. Part of my philosophy of science is in effect a kind of history or sociology of science, but a part of my philosophical work also involves what I think of as characteristically philosophical methods, which are not based on empirical testing. Not so much what I've been talking about to you today, but I do think we can know things in these other ways, but it has turned out, perhaps nobody could reasonably foresee this, but it has turned out that the most reliable and effective way to gain a certain kind of knowledge about the unseen workings of things, of the material world, at any rate, has been the scientific way.
Okay. All right. This next question is, I think, from one of my students. Can you talk about the role of prediction in science?
Yeah, well, a lot of these empirical tests are a case where some theory makes a certain prediction. Einstein's theory predicts that if you photograph the stars during an eclipse, they'll all appear to be slightly moved outwards from where they seem their positions normally. Um, and it's exactly, I said the iron rule lays down a kind of a standard for what counts as empirical testing, and it's exactly that kind of prediction, checking to see if those predictions come out correctly, that makes for a typical test. Not all tests, though, are about prediction. So, for example, a very important, and this is typical of something that took a long time, was kind of inherently boring yet incredibly important for science. A very important part of geological research back in the 19th century, when people was just getting the history of the Earth sorted out, was just looking at rock faces, looking at places where people had dug canals,
Mhm.
or the equivalent of, I guess, road cuts, more for railways in those days, and compiling big maps of geological formations. So that's not really about any theory making a prediction, but it's still amassing a big set of observational data. Likewise, a little bit later in the 20th century, mapping the floor of the ocean became very important for the development of plate tectonics. But again, it wasn't so much a matter of testing a particular prediction as building up a kind of just a picture of what's out there,
Right.
even in advance of having any theory that could predict it.
Okay, this next question is from Laura, who asked this. Do scientists still believe in beauty being a contributor in scientific theories? Would beauty be thought of as something akin to religion, which often clashes with empirical observation?
Well, I don't think so. I mean, I should say what I don't think. I think that I quoted a few physicists there on how important beauty is to them in terms of seeing the truth, and they they take it, seem to me to take it very seriously indeed. So I see these kind of aesthetic arguments, at least in some sciences, maybe not all sciences, but in this kind of fundamental physical research, as being quite compatible with scientific inquiry. It's just that, and this is what seems quite perverse, it's just that these considerations can't be actually published. The very things that have convinced you of the truth of your ideas you can't use those considerations to convince other people. So there is a kind of a connection there. I would say the same also actually about, this, again, this is not always the case, but in some cases, I think scientists' theological convictions have helped them to arrive at fruitful ideas. Of course, not always, but sometimes, and that in those cases, even a kind of theological reasoning has been helpful to scientists. But again, they haven't been able to appeal to this in their public arguments, and likewise philosophical considerations about, for example, the interpretation of quantum mechanics. Uh, all of this can go on in the scientist's head. Not all of it is going to work out, and sometimes it might hinder rather than help the scientist come to a really fruitful theory. But that's all okay. It's all part of science. It's all outside the domain that's legislated by the Iron Rule, because it's private. It's in the scientist's head. It's just when it comes to publication that it's a matter of empirical evidence only.
Well, I'm skipping ahead for a few students, but go ahead and say it. Do science and religion conflict in your view?
Well, clearly, there are a huge range of religious views out there, and in some cases, science and religion certainly have conflicted and do conflict. So I myself think that there's overwhelming evidence, for example, against the views of the young Earth creationists. And that would be a case where I see there as being a really serious conflict.
Right.
On the other hand, there are many religious views that I think are quite compatible with the science we have right now.
Right. Okay. Next question is, how did scientists do during the COVID crisis?
Aha, that's a great question. I think actually not so badly. I think that the process of scientific inquiry operated the way it was supposed to. The thing that went most badly wrong, which is a tricky thing even under the best of circumstances, was, if you like it, the interface between science and society. So scientific knowledge tends to proceed in a very messy and disorganized way.
Yeah.
What you have is, it's not as if there's some kind of central clearinghouse for scientific knowledge.
Right.
Rather, what scientific knowledge is really nothing over and above the opinions of all of the scientists who are trying to solve the problems they're trying to solve at any given time. And inevitably what you have, and this was, I think we all saw this happening as the pandemic unfolded, is you have many different views, because a lot of the evidence, these research programs are at an early stage. Some scientists are saying, well, the best thing we have to go on is the behavior of other coronaviruses, while other scientists are saying, no, let's look at the patterns of transmission and give those more weight. And everyone thinks that these considerations deserve some weight. But until more evidence arrives, you can get a lot of diversity of opinion. And there's nothing in the structure of science itself to take the next step and turn that diversity into even a unified presentation of the current state of uncertainty. On top of that, of course, you have for various social and political reasons, you have bodies like the CDC and the WHO may feel like they have to give particularly clear or simple guidance, that a full appreciation of the complexities might backfire, and so on. So it was a complicated and tricky situation, but I do think it's a difficult problem, and clearly, to some extent, some of there were things were not done as well as they could have been. Simply to present to the general public a kind of a frank, accurate assessment of exactly what we know and what we don't know.
Yeah. Okay. Yeah. And I felt like they did pretty well. I mean, just in coming up with a vaccine, good heavens. I mean, that was pretty remarkable.
That was amazing. Yeah. And if you're someone who followed things very closely, and you kind of, as it were, do that work yourself of interpreting the science, then you could definitely, I think you probably feel a little bit less confused about what was going on than most members of the general public, who understandably don't have the resources or the background knowledge to do that.
Well, or you want to possess a certain certainty that's just not going to be there in real time. I mean, you're talking a moment ago about it's 100 years after Einstein's theory that, it just takes time.
Yeah.
Okay, so the next question, probably again from one of my students, is the Webb telescope an example of the iron rule?
Yeah, that's a great example of something that Of course, it took, well, many of these big science things take a lot longer than they're
Yeah,
supposed to the point where you kind of wonder
yeah, yeah.
whether any there's really any prospect of anything coming in on time. But that's a great example of um, science putting so much emphasis on gathering empirical information, in this case, making observations, not performing experiments, that a group of people is willing to throw themselves into a project that took, how many years was it? I mean, it's
Oh gosh,
20
20 years
years.
or so,
Yeah,
more maybe. Yeah.
20 years or even more. When I read about, some of the setbacks they have, um,
Mhm.
everything has to work. Of course, everything had to work perfectly with no possibility of going in there to kind of give it a bit of a kick to
Right.
get something unfolding that got stuck. And that they just had to go back again and again and tweak things and get them right. Then something else would go wrong, and then have to go back and rejig. I mean, I observed this, of course, from very far away. That it must be so frustrating to be an engineer working on a project like that, and yet you have this sense that this is the way science is done. That's I think that is the iron rule. The iron rule's kind of glorification of observable fact as the one true route to finding out the truth is plays a big role in kind of getting people out of bed every day to deal with these kinds of problems, frustrations, setbacks.
Right. Right. Okay. The next question comes from one of my colleagues, an English colleague, Susan Cotton. She says, when you were speaking of the motivation of scientists, it seems to me that perhaps that same phrasing could apply in other fields. For example, rules of scholarship for scholars in other fields to pursue their interests. Would you agree or comment, please?
Yeah, I think that's right. I think all in every department of the university, in every part of academia, we have our rules for scholarly communication. That is for publishing in the journals. I don't see anything in the humanities that plays quite the remarkable role
Right.
that the iron rule plays in science. In my own field of philosophy, I feel like although there are various rules and customs and so on, there's a sense in which, when it comes to actually arguing for our views, anything goes.
Yeah. Yeah.
Uh, and that's a wonderful thing. I mean, that's probably why I'm a philosopher and not a scientist. At the same time, I find myself in this position where I see the way the scientists are doing it, although it's shackled in a certain way. I have to feel a little bit chagrined and envious of the success that scientists have had
Yeah.
as a consequence.
Yeah, I do think with historians, there's some truth in what you say, but with historians, it does your argument has to be anchored very strongly to archival evidence, and if it's not going to be taken very seriously. Uh,
Right.
but it also operates on a consensual basis as well, which is something that scientists do too. That in a way, science is what scientists do, in a sense, you know. So, and history is what historians do. So, okay, the next question comes from Heather, a biologist, and she says, "Isn't it actually irrational to claim that an idea is true if you can't reproduce it, regardless of who you are, your personal background, your perspectives, your priorities, and so on?"
So isn't it irrational to not follow the iron rule, perhaps? The rational thing
Yeah.
is to check everything against the evidence. Well, I think that's the principle that Aristotle laid out. Uh, he was saying we've got to check our theories against the evidence, but in saying that, he wasn't saying that's all we should do. So the iron rule takes things a step further and says, don't just check your theory against the evidence. That's the only thing you should do. None of the other reasons you have for believing it should make it into the public arena. So on the one hand, you have something very rational going on, that is taking the evidence into account. I mean, really rationally magnified to the nth degree, and this is what makes science so incredibly successful. On the other hand, the motivation to pursue that line is coming from a kind of narrowness that is irrational. So
Yeah.
it's not there's not a single scale here. There are several different interlocking parts, one of them supremely rational and the other, in a certain sense, less so.
Okay, we've got time maybe for two more questions, Michael. And the next question is from Faith. And she wanted to know, or if you could elaborate on the role of theory in science. Do these theories arise after the empirical observation, or do they often arise before empirical observation?
Well, it varies. It varies a lot. With something like Einstein's theory of relativity, really, and the theory is very much at the beginning. Einstein had one known phenomenon he could test his theory against, to do with the orbit of the planet Mercury. But other than that, the ways in which his theory would diverge from Newton's would show up in facts that simply hadn't been unearthed. On the other hand, I was just talking a few minutes ago about geology and the construction of the maps of the strata in the earth, and the mapping of the ocean floor, and so on. And here the theory was following along, I think, behind the facts. So it can very much be both. And as much evidence as I've put on the facts and testing and so on, it's also, of course, crucial to have theories and to develop theories if you don't have them. And I don't want to in any way discount that as an equally important part of science. But there, I think there's nothing like the iron rule kind of prescribing a certain way of proceeding. You come up with your theories ahead of time, or wait for the facts and then come up with your theories. That aspect of science, the theorizing aspect of science, is more of a kind of a anything goes pursuit.
Yeah, it's kind of interesting because I think, for example, Darwin, once he came up with his theory that species change, then he said, I have a theory by which to work, and it helped unlock the evidence that was in front of him in a different way, but that may not always be the case, I suppose. Okay, last question. How have scientists reacted to your book?
That's a good question too. So some scientists have said to me, I'll start with the best reactions from my point of view, have said, if you're right, this is what I've been doing all along. And in some level, I know I've been doing this. I know, of course, the iron rule is hemming me in, is focusing me in a certain direction. But until I read your book, I hadn't kind of, as it were, seen what I was doing at that theoretical level. Not all of them are quite so happy, I think. Of course, calling something irrational is a way to get people's backs up. I know that. I'm trying to get people's attention. But I do want to emphasize that I'm not saying scientists are irrational. I don't think that at all. It's more, there's something about the system that builds in a certain irrationality. But being a scientist is not irrational. Doing science is not irrational. Spending a lot of money in our society, as we do, on doing science is not irrational. It's more a kind of it's more that the rules of the game are themselves irrational. So when I talk to the scientists who bristle a little bit, I try to get them to see that.
Yeah. Well, this has been a very, very interesting talk. We've got a couple of messages in the chat saying thank you. It's been an hour well spent. I want to encourage everybody again to go out and buy The Knowledge Machine, How Irrationality Created Modern Science. It's an excellent book, again, out in paperback. And Michael, thank you for your time. And I hope everybody in the audience has a wonderful afternoon and a wonderful weekend. Thank you.
Well, thanks, John. This has been a lot of fun for me, at least.
Yeah, well, good. I'm glad to hear that. It was a good talk. Your slides were excellent. So, yeah, thanks a lot.
Be sure to follow us on social media at Facebook, Twitter, and Instagram. Like this video, leave a comment, and hit that subscribe button to be notified about our latest content.